Okay, it seems there's some confusion about null space, range space, generalized null space, etc. So let me go through a problem and try to give you some techniques that will help you do this in general. Right. So here we have a transformation, and in the book, I think he calls transformations T or something. Let me just call this, I'll call it, I can't call it A, B, or C. Let me just call it Z. What the heck? Z. Transformation Z. So I want to find the null space, range space, and chain of null spaces, chain of range spaces. So find chain of null spaces and range spaces. All right, so what's happening with this matrix here? First of all, I would say that it's probably easier and better just to think of this in terms of component vectors and not polynomials. I think that's going to make it easier to conceive, and it also will standardize all of these problems, whether you're using polynomials or functions or some other kind of vector space, reduces to the same thing. So let's change this to a matrix vector problem. So let's find the matrix for the transformation. Let's do that. Now, we have to choose a basis. So let's choose the standard basis. This is something that should be able to do very easily. 1x squared is this nice standard basis. So if I want to get the matrix, I need to know what it does to each one of these basis vectors. Okay, let's see what the matrix does to 1, 0, 0. Now, if I put in 1, 0, 0, that means I have A equals 1, B equals 0, C equals 0. You see, I get out a 1 here, and a 1 here, and then a 0. So that means 1 times the first basis vector plus 1 times the second basis vector. 0. Now, what happens if I put in 0, 1, 0? Let's erase this. If I put in 0, 1, 0, what happens? I'm using the fact, again, that if I put in a standard basis vector here, it will pull out the relevant column in the matrix. Okay, so when I apply this matrix to this vector here, the result is going to be the second column of this matrix. So let's see, if I put 0, 1, 0 in, then I get, that's A equals 0, B equals 1, C equals 0. Equals 0, B equals 1, so I get a 1 out. 0, B equals 1, C equals 0, so I get a 1 here, and I get 0. Now, let me just do this one by hand. Suppose I put in 0, 0, 1. If I put that in, then A equals 1, A equals 0, B equals 0, C equals 1. I get a 0 here, I get a 1 here. 0, 1, 0. So here's my matrix, which I'll call capital A, or capital Z. What's that? Z is. Okay. So the range space of the transformation corresponds to the range of this matrix. The null space of the transformation corresponds to the null space of this matrix. And that's stuff that you've seen before. So if you're confident about what we learned in the first few weeks, then you should be able to do this as well. Okay, so the range space of small z comes from the range space, the range of z, matrix big Z. Okay, and then null space null space of Z. Okay. All right, so let's take a look at the range. The range of this matrix, Now, the range of Z is just the range of the column space. So the span of the columns, rather. And you can see these first two columns are linearly dependent. And this second column is linearly independent. So the dimension of the range is 2. And also you can see that these two vectors span all vectors that have non-zero first two components. So the span of the columns, so this would be the span of 1, 0, 0, and 0, 1, 0. Right, I could put 1, 1, 0 here and 0, 1, 0, but this span is the same. So that gives me, so that means the range of small z is equal to the span of 1x. You could also write it this way, equals a plus bx. Okay, so that's the range space of Z. What about the null space? Well, the null space is the null space of the matrix. Say null space of matrix. Now, to find the null space, you solve the homogeneous equation. So you can do that using row reduction. Sorry, there's a 1 there. 0, 0. Row reduction will give me R2 minus R1. Gives me 1, 1, 0, and then this would be 0, 0. All right, so if we change this into equations, that would be the same thing as saying, well, a plus b equals 0 and c equals 0, right? So for instance, this is the span of 1 minus 1, 0. Pretty clear that I could choose b as minus 1 and then a would be 1. So the null space of the transformation z, small z, is equal to a minus bx. Okay. All right. So again, that's the null space is what maps to 0. Now let's consider the next stage. So we want the range and null space of z squared. Now, of course, the straightforward way to do this is simply to square the matrix. But there's another way to do it, or even more than one other way. So let's look at the range space. All right. So I'll make this statement and then justify it. The basis of the range of z squared can be obtained by applying z to the basis of the range of z. Right. So the picture is that here we have a basis first, and then you apply z. When you apply z to this basis, you will get a basis of the range of z. Okay, this spans everything in the range. Now, when you apply z again, you're applying z only to this subspace. Okay? So the basis here must go to a basis here. All right, basis goes to basis goes to basis. Now we have a basis of the range of z. This basis was, I'm going to use the component form, 1, 0, 0, and 0, 0, 1, 0, 1, 0. Now, if I apply z to that, if I apply z to this first vector, well, that's just going to give me the first column of z. Remember, that's just what I did at the beginning. Here, the range of z only includes the first two basis vectors in the standard basis. So if I apply z to this column vector, it's going to give me the first column of z. So that's going to give me, you remember what that was. If I apply 1, 0, 0 to this matrix, I'm going to get 1, 1, 0. And while I'm up here, if I apply 0, 1, 0 to this matrix, I'll get the same vector, 1, 1, 0. So in fact, it's going to be equal to 1, 1, 0. That's somewhat easier than finding z squared. So that means that that's my basis for z squared. So the range of z is equal to the span of 1, 1, 0. And that means the range of small z is equal to this set, I can write it this way, a times 1 plus x. All right? Now, what about the null space? We can do this similar kind of collapsing. So null space of z. So that means that is the set of vectors such that z applied to set of vectors x such that z applied to zx is equal to 0. I shouldn't use x. Let's say v, because I use vector class. Z applied to zv is equal to 0. So what does that mean? That's true. That means that zv is in the null space of z. Okay. So that means that and I have a basis for the null space. Right? What was my null space? So my null space was a minus bx or 1 minus 1, 0. So that means that zv must be some multiple of 1 minus 1, 0. Now, you can see that this multiple will only change the v by a multiplier. So I can solve, let me solve zv is equal to 1 minus 1. So we choose k equals 1. K equals 1. If I had another value of k, then v would just be multiplied by the same constant. So now I have an inhomogeneous equation, not a homogeneous equation. But I can solve it the same way. If you remember, my matrix was 1, 1, 0, 1, 1, 1. And now I have 1 minus 1, like this. I can use the same operation, R2 minus R1. Here I have 1, 1, 0, 1. And here I have 0, 0, 1, minus 2. Did I do this right? Yeah, that's fine. Okay, that's fine. Yes, okay, and then 0, 0, 0. Okay, so what's my solution? If I'm using ABC, I'm going to have A plus B equals 1 and C equals minus 2. C equals minus 2. So I can choose, for instance, I can choose B equal 1, A equals 0. Now you might ask, why can I make a choice? Well, because the difference between any two solutions is going to be a homogeneous solution, and I already have the homogeneous solution. I already got the homogeneous solution. I know the homogeneous solution is 1 minus 1, 0. So my vector is 0, 1, minus 2. And this is a vector in the null space of z squared. Now the null space of z squared also includes the null space of z. Okay. also includes that null space. So that was equal to 1 minus 1, 0. So that means the null space of z squared is equal to, let's see, it's equal to the span of 1 minus 1, 0 and 0, 1 minus. And if I wanted to do null of small z, it's equal to the span of, so I can say a times 1 minus x plus b times x minus 2x squared. Okay, so that's the general null space of z squared. So let's think about what about z cubed? Let's consider that for a minute. Well, I can use the same method, right? The range of z cubed as a basis is equal to z applied to basis of range of z squared. Okay, what's my range of z squared? Whoops, I should have put a square here. That should be a square. All right, so if I apply z to this vector here, 1, 1, 0. Remember this matrix here is 1, 1, 0, 1, 1, 1, 0, 1. This, and then I have 1, 1, 0. That's equal to 2, 2, 0. Okay, so it's the same. It hasn't changed. Okay, so that means that the range of z cubed is equal to so it's equal to the range of z squared. All right. Now, if the range is the same, then the null space is also going to be the same. But we could do so. That means that this implies that the null space of z cubed must be equal to the null space of z squared. We can also find that directly. So our null space of z squared was this here, 1, 1 minus 1, 0, and 0, 1 minus 2. So we could simply solve z times v is equal to 1 minus 1, 0, and zv is equal to 0, 1 minus 2. And the solutions of these will give me a basis of the null space of z cubed. These are in the null space of z squared. So this is a basis for the null space of z squared. And if I try to solve that, well, we can go through the motions here, see that we get something consistent. So this was 1, 1, 0, 1, 1, 1, 1 minus 1. I think I solved this one already. And we have this one here, 1, 1, 0, 1, 1, 1, 1. So sorry, this would be 1, 1, 1. This should be 0, and this should be 1, and this should be 2. So 1 there. So I seem to remember that this one gave me this as a solution. And then if I try to solve this one, well, let's just do it, right? If we do that row operation, if I take R2 minus R1, I'm going to get 1, 1, 0, 1, 0, 0, 1, minus 2. Yeah, that's what I got before. So the solution here is going to be some constant times 0, 1, minus 2. And then if I try to solve this, you can see that I'm going to get c equals 0. Well, I can do the same reduction, right? 1, 1, 0, 1, 0, 0, 1, minus 2, and then 0, 0, 0, 2. So this is telling me c equals 0. Right? And if c equals 0, then here I've got, let's see, and it's going to tell me, this is kind of messy. This should be 0, 1, 0, oh, 0 minus 2 minus 2, okay. So this is telling me C equals 0. This is telling me C equals minus 2. So, and C equal minus 2, so there's no solution. So that so this confirms that the null space of Z cubed is equal to the null space of Z squared. All right, so just to recap, important concept here. When you have a transformation, express it as a matrix. Find a good basis, express it as a matrix. Once you've expressed it as a matrix, usually the problems that you'll have can reduce to some of the basic problems we had in the first few weeks. Null space of this transformation is the null space of this matrix. The range space is the range of this matrix. Null space of a matrix, that's the solution to the homogeneous equation. Range of a matrix, that's the span of the columns. Then this new thing, if I want to find the range of the matrix squared, I simply apply the matrix to a basis of the range. If I want to find the null space, I simply solve the equation for the Z times V equals a basis in the null space of Z. To just kind of ladder yourself up once you have one of them. One thing to notice here is that the eigenvectors with non-zero eigenvalues are always non-zero eigenvalues are always in the generalized. When I say non-zero eigenvectors, I mean eigenvectors with non-zero eigenvalues. Let me just say this here, eigenvectors with non-zero eigenvalues. So if you have a matrix that's diagonalizable, then that shows you that, well, you already know that if the matrix is non-singular, and the generalized range is the entire space. But if it's diagonalizable, some of the eigenvalues are 0, then you know that the non-zero eigenvalues are giving you the generalized range. So I'll stop there.